Hi, this is your third podcast on significant figures, and today we're just going to be discussing the rules behind significant figures and what they are, why we care about them in science. This goes under the unit Understanding and Communicating Scientific Measurements. Understanding and Communicating Scientific Measurements. So, here we go. All right, what are our objectives? First of all, we need to know what significant figures are. Then we need to understand why we use them. Then we have to be able to identify both certain and uncertain digits in a measurement, the ones we're sure about and the ones that are estimated. And using a list of rules, we want to be able to identify which digits in a measurement are significant. So what are the expectations of you during this podcast? Well, using your Cornell notes, please pause this podcast when you need to and record the key ideas. And of course, any questions you have, make sure that you record those in the margins and bring them to class with you. At the end of this PowerPoint on slides 9 and 10, I not only want you to record the answers to your questions, I just want you to record the number that's listed, and it'll be 1 through 10. Make sure you write the measurement that's given and then the answers to the problems. And then be ready to discuss and apply the principle of significant figures in class when we meet next. Okay, so what are significant figures? Significant figures are actually all of the measured digits in a particular value plus one estimated digit. So when we look at a measurement, significant figures really reflect all those digits which we know for sure and one digit that we are kind of sketchy on. So what does that mean? Well, let's look at this rectangle here. Just a very basic rectangle, and I put some dimensions on the top and on the side of this so you can see what the length and the width of this rectangle are in metric. So what you'll notice at the top here is that we have the measurement 5.76 centimeters. Okay, well, that's great. So if we're looking at significant figures, all of these figures are significant. The 5, the 7, and the 6 are significant. What this really means, though, is if we look at it a little bit more closely and we think of it scientifically, it means that this 5 right here is a definite 5. We have 5 centimeters in this measurement because our measuring device tells us that. We also know for certain that this 7 is exact. We know this because our measuring device tells us this. But what we also know, because we're in science class and we're using significant figures properly, is this 6 right here is actually a significant figure, but this is our estimated value. In science, we don't keep estimating values out, so it would be kind of ridiculous for me to say, okay, I know this for certain, I've got a 5. I know a 7 for certain, I know a 6, kind of, so then maybe I'll add a 4, maybe I'll add a 3, and maybe I'll add a 1. Well, that would mean I would have a lot of garbage on this number that really isn't true at all. And it can't really be true if this 6 right here is estimated. So that's what we're kind of thinking. So if I have this measuring device, and this measuring device measures to the nearest ones place, and I'm estimating, it measures to the nearest tenths place, and I'm estimating to the hundredths place, I can't use that measuring device and say, well, this is 5.8 centimeters long. Or it's 5.7684 centimeters long, because the number that I actually use has to reflect the accuracy of my measuring device. So once again, if you look at the width of this particular rectangle here, what I'd like you to notice is that it also goes to the hundredths place. So my measuring device measures exactly to the tenths place. So it has tenths place divisions, and this last number here, this 2, is one estimated value. So this measuring device, since it can measure to really an estimation, the hundredths place, it would be kind of unrealistic to just say, yeah, we got a centimeter, or oh yeah, we have 1.32222 centimeters. That's not realistic. If this too is estimated, it would be kind of silly to put these numbers on there. And in science, it would actually be lying in a way, because we're saying that our measuring instrument then is going to be exact to the tenths, hundredths, thousands, 10,000ths, to the 100,000th place. And that's just not going to happen with a regular ruler, standard metric ruler. So maybe you have the idea of what we're doing here. So why do we use these? Well, when significant figures are used properly, they not only communicate the quantity of a sample of material, but they also reflect the precision of the measuring device used. Is the measuring device really precise? Does it have a lot of graduations? Is it highly calibrated? Does it have a lot of potential to measure exactly? Or is it kind of a lame measuring instrument? So it tells us not only what the value of the quantity is, but how precise the measuring device is that we use. So let's look at this bathroom scale here. And I know it's kind of hard to see, but what you can see is we have a 160 here, so this would be a 170, this would be a 180. So I bet you could guess here there's probably 9 ticks between here, and each of those measures a pound. So you hop on this scale here and you look at it and you go, oh, wow, okay, 100 in, and you look real close and you go, well, maybe 160. Okay, maybe it's a little bit shy of 160. Maybe it's a little bit more than 160. So at best you might be able to say, oh, I don't want to weigh 160, so I'm going to say it's 159.8 pounds, because that makes you feel a little bit better. Okay, but you can't keep estimating out. You can estimate one place. So let's look at this measuring device. This is an analytical balance here. And what I'd like you to know is it's kind of hard to see here, but here is a decimal point. And what that means is that this analytical balance would measure not to the tenths place or the hundredths or the thousands, but this dude here would actually measure to the 10,000th place. Well, we're looking at something that's entirely different here. So let's say we placed an object on this balance and it came up as 3.176 grams. 4 places after the decimal here. Well, what that means is that this is exact, and this one might be a little bit off. And I'm sure you've all put things on a balance or gotten on a digital scale and seen the last number kind of flicker back and forth, maybe 5.4, 5.4, 5.4, and then maybe it'll settle in. But that tells us that that's estimated and perhaps a little bit uncertain. Okay. So, but why do we really care? Well, the reason we really care about this is so that we as scientists and also the scientific community can communicate really clearly with each other, and also very effectively. And we need to know that the numbers that we're looking at, the measurements that we're looking at, have value, that they're not big fat lies that somebody made up. If you use a lot more digits than your measuring device allows you to use, well, it actually, in essence, is a lie. And the same thing if you were to take a measuring device that's highly accurate and you used hardly any digits to convey that measurement, you would also be lying. So, uncertainty. Estimated digits, which are always the last significant figure in a measurement, reflect uncertainty. And so if you look at this number here, all I'm saying is, in this particular measurement, since this 5 is estimated and it's the last digit, that is our uncertain digit. Makes sense. All the other digits that go before the last number or precede the uncertain digit are considered to be exact, and therefore they are certain. What you have to know, though, is all of these numbers that you see right here are significant. All of these certain digits plus the uncertain, all of these certain digits plus the uncertain, they are all significant. And in case you're wondering what this unit is here, it's a light year. So which of the digits below are certain and which are uncertain? So how about this? Well, if we look at this, our last digit is a 0 in this case. That means this is an estimated value. So what that means is in this measurement, 5.340 kilograms, that the 5 is certain, so I'll put a C up here, the 3 is certain, the 4 is certain, and the 0 is uncertain. So in total we have 4 significant digits. 3 certain, 1 uncertain. So right here, once again, we have certain, 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 and remember you can only estimate one digit, so it's the last one, and this one's uncertain. So we have 6 digits that we know are true, and we have one uncertain digit for a total of 7 significant figures. And the last one here, the 6, of course, is uncertain, and everything that precedes that is certain. So we have 4 certain significant figures and 1 uncertain. So here are a list of rules, and you need to definitely pause and record at this point some notes. These are some rules that you will have to know. And you're not going to really have these in front of you, but as you start to use them, you're just going to learn them as you apply them. So our first rule is that anything that's a non-zero digit in a measured value, we count as being significant. So if you look at this and you see all of these numbers here, there's no numbers that are zeros. What that means is that every single one of them is a measured or an estimated value, and they are all significant. So in this first measurement, we have 4 significant figures. Here we have 6, and here we have 2, 4, 6, 8, 10. 10 significant figures. So all non-zero digits are significant. One or more final zeros after the decimal point are significant. So what you can see here is that after the decimal point, here's the decimal point, after the decimal point, you have some zeros. Well, those zeros are there because they're either estimated or they are measured. And so if these zeros appear after the decimal, to the right of the decimal, then they are regarded as being significant figures. Now, in this case, the 0 is uncertain, but again, it's still significant. So we have 3 significant figures here, 5, and here we've got 6. Our third rule, zeros between 2 other significant figures are also significant. So here all we have to do is look for the non-zero digits. We have 2 of those. And these 2 zeros are between, so that means they're significant. So we have 4 significant figures here. This 0 is between non-zero digits, or digits that are significant, so that means that all of these digits are also significant. And then the same thing here. The zeros appear between other non-zero digits, which are significant, so everything's significant. Okay. The last rule says zeros used as placeholders are not significant. Now here's a little caveat. If there's a decimal point present, after a 0 that appears in the ones place, then all digits are significant. Okay, so here we have some placeholders. Okay, so what this means is that this 4 is measured and it's exact, but what that also means is that since the last 2 zeros are not significant, this 5 is uncertain. So really our measurement could be 4,400 yards or it could be 4,600 yards. But we just can't leave out those zeros. We have to put them in there as placeholders. So what I have here are 2 significant figures. The 4 and the 5 are significant. Okay, now in this particular measurement here, we have 3 leading zeros, one that's just there because it's there, just so we don't lose a decimal. But then we have these 2 dudes that are just kind of holding our place for it. The 7 is measured and it's exact. The 5 is estimated, so we have 2 significant figures. Now here's our caveat. You see how this number is not written as 610 like this? If this were written as 610 with no decimal point, then we would only have 2 significant figures because the 0 right here is a placeholder. However, since we have a decimal point right here, what that tells us is, ooh, the 6 is measured and it's exact, the 1 is measured and it's exact, and the zeros actually are uncertain digit, but it's estimated, so we regard it as being significant. So you'll need to pause and make sure that you record those rules. You'll need them. You also have a reference sheet that I gave you in class that has these same rules on it, but no examples. So you can use that as well, but make sure you record these in your Cornell notes. Okay, so here we have a table, and what I'm going to do here is make sure you get all these down. This is slide number 9. What we're going to do is we're going to count significant figures. So if I count here, I've got non-zero digits, 1, 2, 3, 4, and I've got a final 0 after the decimal. That means I've got 5 significant figures.